Hello and welcome to the problem-solving session on current and resistance problems. This accompanies chapter 22 in the textbook. So the first problem we're going to look at says a potential difference of 1.2 volts will be applied to a 33 meter length of 18 gauge copper wire. Calculate the current that will flow through the wire. So you have a piece of wire and we know a few things about it. We know that it has a diameter of 0.04 inches, has a length of 33 meters, so clearly my sketch is not to scale. And then we're applying a potential difference of 1.2 volts to it. So we could imagine, for example, that we had a 1.2 volt battery. And we connected it to each end of this wire. How much current will flow through the wire? Well, if you've read chapter 22 or you've watched the lecture on this, you've seen that the resistance of a wire or any conductor, actually I guess any material for that matter, depends on three physical parameters. One is known as the resistivity of the material. So that's a constant of the material, and it's symbolized by the Greek letter rho in our textbook. It's basically a number that tells you how freely charge will flow through the material. So resistivities for conductors are quite low. Resistivities for insulators are pretty high. It also depends on the length of the wire, and the longer the wire, the harder it is for charges to flow through it. So increasing length increases the resistance. And the final piece it depends on is the cross-sectional area. And the bigger the cross-sectional area, the easier it is for charge to flow through this wire. Just like if you think about a pipe with water flowing through, the larger diameter pipe, the easier it is for water to push through that system. So we know the length that's given directly to us. We don't know the area quite, but we do know the diameter. And recall that the area, the surface area for a circle is pi r squared. So that means we can rewrite our resistance as resistivity times length over pi times half that diameter squared in the denominator. We don't know the resistivity, but in this particular instance you can look it up. There's a table of resistivities in chapter 22 of the Knight textbook. Alternately, you can Google. If this were an exam question, that resistivity would be given to you. You wouldn't be expected to know it. But I looked up in the Knight text, and he lists the resistivity of copper as 1.7 times 10 to the negative 8th ohm meters. We're almost ready to plug in, but notice this is in meters, the length is in meters, but the diameter gives us to in inches, and we're going to need everything to be in SI units if we're going to work out a resistance in the standard SI units of ohms. So I used the Google convert. You can also realize that 2.54 centimeters is the same as 1 inch. That means 0.0400 inches is 0.001016 meters. Again, you can in Google just type in convert 0.04 inches to meters and it'll pop that number out for you. So that means our resistance is equal to, let's put all those numbers in, 1.7 times 10 to the negative 8 ohm meters. Length is 33 meters, and then in the denominator we have pi, and we have a diameter of 0.001016 meters. Divide that by 2 to get the radius, square that all, And notice, unit-wise, we're going to have meters times meters up here. We're going to have meters squared down here. All the meter units are going to cancel and leave us with units of ohms. If you punch that all into the calculator, you get a resistance of 0.692 ohms. So that was part A. Part B says the current, how much current will flow through the wire. Well, we have Ohm's law, which says that the current is directly proportional to the potential difference across something and inversely proportional to the resistance of that object. So we know the potential difference is 1.2 volts. We just calculated the resistance to be 0.692 ohms, and if you divide 1.2 by 0.692, you find the current, which is 1.73 amps. Problem 2, similar problem in dealing with resistivity. A wire of nichrome, a nickel chromium iron alloy commonly used in heating elements. It's 1 meter long, 1 square millimeter in cross-sectional area. It carries a current of 4 amps when a potential difference of 2 volts is applied end to end here. So if we have some wire, again, this sketch is not to scale, but we know the cross-sectional area here is 1 square millimeter. The length of this wire is 1 meter. Oh, didn't get all the way to the end there. And at some point, we're carrying a current of 4 amps, and that happens when we've hooked it up to a battery that has a potential difference of 2 volts. So connect that over to here, connect that over there. All right. What is the resistivity of nichrome? Well, here we need to put together two relationships that we've seen on the previous problem. We know that the resistance of a wire is equal to its resistivity times its length over its cross-sectional area. From Ohm's law, which I always write as current is the potential difference divided by the resistance, we can get that resistance equals the potential difference divided by the current. And you can put those two things together to say that resistivity times length over area must equal potential difference over current, because both are equal to the resistance. And that means that resistivity is equal to the potential difference times the cross-sectional area divided by the current times the length. And now it's just a matter of plugging things in, though we do have to watch out for one conversion here. So I have a potential difference of 2 volts. I have a cross-sectional area of 1 square millimeter, and that's what I'm going to need to convert. I'm going to come back to that momentarily. The current that I have flowing through is in standard units, 4 amps. The length of the wire is 1 meter. And so here's where you have to put a conversion in. I'm going to do it this way. I know that there are, 1 meter is equivalent to 1,000 millimeters. But because I'm converting a meter squared, I've got to square this conversion factor as well, which means I need to ultimately divide the 1 by a million in order to get this converted into square meters. But everything else is pretty friendly-wise, number-wise. So this whole thing is 1 times 10 to the minus 6. If I divide that by 1, still 1 times 10 to the minus 6. And then times 2 divided by 4 is going to cut that in half. and we find that the resistivity of this particular nichrome alloy is 5 times 10 to the minus 7, and the units are typically expressed in ohm meters. When we did this in class, we were looking at the table in the night text of resistivities, and if you look up that, nichrome I think is about 3 times as resistive in the night text, but we Googled and satisfied ourselves that because nichrome is an alloy, has different compositions of nickel, chromium, and iron in it, depending on the mix there, you can alter the resistivity of that material. Problem 3 gave us a simple circuit and a graph. We have a 20 ohm resistor connected to a battery. And here we see the increase in thermal energy in the resistor as a function of time. The vertical scale is set by 2.5 millijoules. So this value right here is 2.5 millijoules. Horizontal scale is set by 4 seconds. So this time here is 4 seconds. Not right at the end, which is a little curveball they throw us on this particular problem. So how do we approach this? Well, recall back in Physics 1, you should have learned about power. And power, most generally, sometimes it's introduced as work done over time. Other times you see it as energy converted or energy dissipated over time. And that second one is probably more useful here. The resistor is converting electrical energy into thermal energy. So that energy is being dissipated or transformed by that resistor. And we know how much energy and how much time from the graph. Namely, power is going to be the slope of our graph right here. So if we take on that graph, let's see if we can figure out what the slope of that is, or the change in energy over a change in time. So there's a couple ways you can do this. You can either take the time and figure out, okay, at 4 seconds, I'm over here on the energy axis, and if I'm counting hash marks, this must be 2 millijoules. Or 2.5 millijoules here must match with, on the time axis, a time of 5 seconds. Either way is going to get you the same result in terms of calculating that slope. So a change in energy over a change in time from this graph is either going to be 2.5 millijoules over 5 seconds or 2 millijoules over 4 seconds. And either way you're going to do that, you're going to get 0.5. The units would be millijoules per second. A joule per second is a watt, so this is 0.5 milliwatts, or perhaps more usefully 5 times 10 to the minus 4, because I have to move the decimal. Let's see, 1, 2, 3 more times to get it into watts. Watts. So that's the power that is being dissipated by that resistor. How does that connect to the electric potential across the battery? Well, electric power, and again, this is either in the textbook or in the lecture, but electric power can be shown to be the product of the potential difference across something times the current through it. But you can then use Ohm's law to replace current with voltage over resistance and get an alternate expression for power that is potential difference squared divided by resistance. Or replace voltage with IR and get an expression that is the square of the current times the resistance. It's this middle one that's going to be the most useful to us in this problem. So if I say that power is equal to the potential difference squared over the resistance, then the potential difference is going to be the square root of power times resistance. And if we go ahead and plug in values for that, the potential difference is the square root of 5 times 10 to the negative 4 watts. Resistance, we're told 20 ohms. And if you punch that into the calculator and do it out, actually in here is 0.01. Square root of 0.01 is 0.1. So that would tell you that the voltage of the battery is just a tenth of a volt. And I'm not off the top of my head aware of any actual batteries that are this. Maybe some biomedicine applications have that. But anyhow, that's the solution to this particular problem. And the final problem on this current and resistance problem set, again, used that power definition that we just talked about in the previous problem. It says an unknown resistor is connected between the terminals of a 3-volt battery. Energy is dissipated in the resistor at a rate of 0.54 watts. So we have a battery and a resistor here, and when you send electric current through a resistor, you get heat out of that. So if I connect this in scenario 1, my battery was 3 volts, and I was dissipating energy, or energy was, leaving the resistor in the form of heat at a rate of 0.540 watts. All right, new situation, take that same resistor. So because resistance depends on resistivity, length, and cross-sectional area, if I don't change anything about that and I have the exact same resistor, I don't change the resistance in any way. So take that same resistor, now hook it to a different battery. So this battery only has a potential difference of 1.5 volts. And so the question is, how much power is being dissipated in this new situation? Well, there's a number of ways you can take this on, but all involve the electrical definitions of power. So power is, again, either potential difference times the current, or potential difference squared divided by the resistance, or current squared times the resistance, and any of those will work. The most direct one to answer this question is the middle one, because we now have connected to a potential difference that is half the previous potential difference. And when you have the potential difference, but then you square it, this relationship predicts that the power dissipated is going to be 1/4 of what it was before. And so that power dissipated is, let's see, 1/4 of 0.54 must be 0.135 watts. But there are other ways you can come to that similar conclusion. Take, for example, this first one, voltage times current. Well, we already know that we've cut the voltage in half. But Ohm's law would also tell us if you cut the voltage in half across the same resistor, you are going to cut the current in half that's going to flow through that circuit as well. So half the voltage, half the current, again, predicts 1/4 of the power. Or this one, I cut the current in half. Half the current squared is 1/4 the current, or 1/4 the current squared, right, times the same resistance. And again, that is 1/4 the power that's being dissipated. So each of these three alternate ways of expressing electrical power would lead you to the same conclusion, namely that the power dissipated is 1/4 of what it was previously. So those are the problems we looked at for current and resistance, and those hopefully will set you up for work on problem set number 4, which is available now on Mastering Physics. As always, if you spot an error in these solutions, I would appreciate you letting me know. Thank you.